Well, welcome back. In this session, we're going to be looking at the defense systems of the lung. Now, this is a topic that's not always covered in the first-year medical student course, although I think that's a pity because it's a very important feature of the normal lung, and it's certainly, first, it's a very interesting topic, and secondly, it's extremely important in terms of defenses of the lung against disease. And so we're going to start by looking at the pollutants in the atmosphere that we all have to deal with. And here's a list of the pollutants. At the top we've got carbon monoxide, and of course we're familiar with the physiology of that now. The danger of carbon monoxide is that it combines with hemoglobin. It ties up a lot of the hemoglobin that otherwise should be available for oxygen transport. And another feature is that it increases the oxygen affinity of hemoglobin, so it makes it more difficult for the hemoglobin to unload the oxygen in the periphery of the body. Most of the carbon monoxide comes from automobiles. It is carbon that is not completely oxidized. Instead of carbon dioxide, it becomes carbon monoxide. And the emissions can be reduced using a catalytic converter. The next group are the oxides of sulfur and nitrogen. I like to think of those together because they share a number of features in common. In both cases, when the oxide combines with water, it forms an acid, sulfurous or sulfuric acid, nitrous, nitric acid. And those acids are very toxic. Of course, they're in relatively low concentrations, but even so, they cause inflammation of the mucous membranes. They can cause chronic bronchitis, and they're certainly very active toxic gases. Hydrocarbons are formed, again, mainly in the internal combustion engine. They again represent carbon that's not fully oxidized. They're not toxic in the normal concentrations that we see in the atmosphere, but they become very important in the development of smog, as we'll see in a few minutes. Particulates include soot, other particles, and they are formed often by processes, industrial processes. And finally, we have photochemical oxidants that we'll be going to talk about in a few minutes. They're extremely important because they are the components of smog, which is a serious problem in many environments. So let's look now at the types and the sources of pollutants. As you can see on the left, the carbon monoxide by weight represents 50% of the total load of pollutants. So it's a very large amount of carbon monoxide in the atmosphere. Then, interestingly, you'll see that sulfur oxides, hydrocarbons, and nitrogen oxides have about the same abundance by weight. So that each of them is around about 15%. And then we've got a small amount of suspended particulate matter, only about 5%. Now, what about the sources of these? Well, as I mentioned, most of the carbon monoxide, or most of the pollutants, come from transportation, particularly automobiles. And you know, we often point our finger at an industrial process. We see a photograph in the paper of a smokestack with stuff coming out of the top of it, and we like to point our finger at industry, but in fact, we are responsible for a large amount of the pollutants because of our cars, although the catalytic converters are reducing the emissions to a large extent, and certainly in California, the air is getting cleaner. But you can see that stationary sources, they would be power plants, for example, are responsible for quite a substantial amount of pollutants. These are also oil burning or coal burning or natural gas burning plants. And we have industrial processes, things like manufacturing paint, puts quite a lot of pollutants into the atmosphere if we're not careful, and solid waste disposal and miscellaneous causes, including forest fires. Forest fires put a lot of particulates into the atmosphere. Now, let's turn to photochemical oxidants, which are the components of smog. And this is atmospheric chemistry, which is complicated, and I don't pretend to understand it well. But the upshot is that hydrocarbons, which, as I say, were normally not toxic, produced often by automobiles, and nitrogen oxides, which represent, incidentally, which are produced at very high temperatures when fossil fuels are burnt. Again, the automobile produces nitrogen oxides. When those two come together under the influence of sunlight, and this is high actinic light, this is short wavelength light, which in California we have a great deal of, that produces, through a complex set of reactions, a series of very unpleasant things, including ozone, peroxyacyl nitrate, aldehydes, acrolein, and other components of smog. And there are interesting features about this chemical reaction. One is that it is rather slow. And so what you find is that the effects of smog are often some distance away from where the hydrocarbons are liberated. Let me give you an example. Suppose an oil tanker is unloading fuel in Southern California on the coast. Some of the hydrocarbons are released. Of course, they try not to, but inevitably some of the hydrocarbons are released from the oil. And then they are moved across to the east by the prevailing westerly wind. And by the time, and it maybe a couple of hours elapses, and by the time they get to Riverside County or somewhere like that, you've got a high concentration of smog. So it's rather unfair. The people downstream of the unloading point get most of the smog because it takes some time for the smog to develop. Now, an important feature of pollutants is that there may be, and here's an example of smog, we are all familiar with this kind of picture, is that there may be a temperature inversion. And this often occurs when you've got a low-lying valley, as shown here. Not sure where this is, this may be Los Angeles. A low-lying valley surrounded by mountains. Now, normally the air at the surface of the earth is warmed, and because it's warmed, it becomes the density is decreased and it rises. So warm air rises normally. But occasionally you get a temperature inversion where cold air sits near the surface, and it's not possible for it to be dispersed upwards by the normal thermal effects. And a temperature inversion like that, which particularly likely to occur in a low-lying area, as shown here, that can greatly increase the concentration of smog. Okay, let's move on now to look at the most important type of pollution, and that of course is cigarette smoking. You know, it's funny sometimes to hear people who are complaining about the effects of atmospheric pollution, smog, whatever, and they're puffing away on a cigarette. The concentration of pollutants from cigarette smoking is far greater than you would ever get in a polluted atmosphere. So cigarette smoking is insidious, and I just point out here that cigarette smoke contains a substantial amount of carbon monoxide. A heavy smoker may certainly have 10% of his hemoglobin tied up with carbon monoxide. Cigarette smoke includes things that are loosely called tars. They're cyclic hydrocarbons, and they cause carcinoma of the lung. And it's well established that smoking is the most important cause of chronic bronchitis, emphysema, bronchial carcinoma, and it's very important in coronary heart disease. So I think all of us have a responsibility. Medical students, doctors, paramedical people have a responsibility to get the message out and try to stop our friends from smoking. Here's a graphic example of the cancer death rates from 1930 to 2004, and you can see that most of the cancers haven't changed all that much. Actually, stomach cancer has come down for some reason. The other ones haven't changed all that much, except for lung and bronchus. Look at this increase in the incidence of lung cancer. The good news is that recently there appears to be a falling off of the rate, and that's very good news. I think that must be in part because of the heavy publicity now about the dangers of smoking. And as I say, I think we all have a responsibility to tell people, friends perhaps, or people that we meet, that smoking is highly dangerous. Now let's, well, this is just to show you the effect of a single cigarette on airway function. Actually, this is airway conductance, which is the reciprocal of resistance. So conductance means that there is airway constriction. Look at the effect of smoking a single cigarette on airway conductance. A dramatic effect. Doesn't last all that long, a little over an hour or so, but inhaling cigarette smoke causes inflammation of the airways, and it's a very toxic gas to inhale. Now let's move to the topic of aerosols, because most of the pollutants are in the form of aerosols. What is an aerosol? An aerosol is a cloud of particles which are so small that they remain suspended for a very long time. They are slowly sedimenting, falling, but the weight of individual particles is so little, and the viscous forces that they encounter as they fall are so great that they fall very, very slowly. And in practice, because of convecting phenomena in the atmosphere and so on, they tend to remain in the air for an indefinite period of time. And most of the pollutants are in the form of aerosols. So I'm going to look now at two topics. One is deposition of aerosols in the lung, and after that we'll look at the clearance, the way these aerosols are pulled out of the lung. Now there are three mechanisms of deposition of aerosol in the lung, and these are shown clearly here. The first one is called impaction. Now impaction refers to the behavior of the relatively large particles, over 5 microns in diameter. They can go up to 10, 20 microns or so in diameter. And these deposit because as they move into the upper respiratory tract, they have to turn corners. For example, if you're breathing with your nose, the turbinates in the nose cause the particle to change, cause the air to change its direction quite rapidly. And they spin out of the airstream just like somebody driving a sports car will spin off the road if he goes around a corner too fast. So the centrifugal force of having these relatively large particles turning the corners makes them impact on the surface of the airway. Once they impact, they're trapped. The surface is damp and the particles are trapped on the surface, so they're not released again. And impaction is particularly important in the nasopharynx, as shown here. Even if you're not nose breathing, if you're air breathing, the inspired gas has to turn the corner very rapidly and impaction can occur. And that's an extremely effective way of removing the larger particles, particles over about 5 microns or so. And this slide shows the sites of aerosol deposition, deposition on the vertical axis here, particle diameter here on a log scale, as you can see. And notice that all the particles over about, 3 microns or so, essentially all of them, the vast majority of them are deposited in the nasopharynx. So the nasopharynx is a very effective way of removing these larger particles by the process of impaction. Now, the next mechanism of deposition is sedimentation. Sedimentation simply means settling out. It's a gravitationally determined process. And sedimentation tends to affect the medium-sized airways most. This is because the larger particles are no longer there. They've been removed by impaction. And the very small particles, their sedimentation rate is extremely low, and so they don't sediment so much. And sedimentation particularly tends to occur in the small airways. Why the small airways? Well, probably simply because the distance that they have to go to settle, to fall onto the airway wall, is relatively short. And as I say, this affects the medium-sized particles particularly. By the way, this says representative site. It doesn't mean that you can't have impaction or sedimentation in other sites, but these are the sites that particularly see sedimentation. Small airways particularly tend to see sedimentation. And this brings us to a topic that we have addressed in the past, but it's so important I'm going to mention it again, and that is the evidence that sedimentation of pollutants occurs in the region of the terminal and respiratory bronchioles of the lung. Remember, perhaps way back when we were talking about the mode of gas flow in the lung, we pointed out that particles get down to the respiratory region of the lung, the terminal bronchioles, that's the last of the conducting airways. The air gets down there, the gas gets down there by convection, like pouring beer out of a pitcher, the regular flow like flowing water. But beyond the region of about the terminal bronchioles, the forward velocity of the gas, the inspired gas, by convection is extremely slow. Why is that? Because the area, the combined area of the airways is so great. There are so many of them, the combined area is very great, and therefore, since the same volume is passing each generation, the forward velocity of the gas by convection is very small once you get to this region of the lung. Now, another process takes over for gas transport in the periphery of the lung, and that's diffusion in the gas phase. But the aerosol particles can't diffuse, or rather their diffusion rates are extremely small. You may say, well, they're very small particles, why don't they diffuse? Well, although they're small particles, they're extremely massive compared with the molecules of the gases, nitrogen and oxygen. So their diffusion rates are extremely small. The net result is that they cannot penetrate to the most distal regions of the lung. And here's a very nice image taken from a coal miner's lung. Now, you may have a problem in seeing the acinus. I can see it. The terminal bronchiole is here, and the edge of the acinus is around here. Okay, and so the artist has drawn it up here so we can see it more clearly. But you'll notice that all the coal dust is seen in the center of the acinus, and that the periphery is largely spared. Now, I just should make an additional statement, and that is the fact that we see the dust here after death doesn't necessarily mean that some of it hasn't been moved here during life. But the fact is that we know that this is where the pollutants settle out, and it's extremely important from the point of view of lung disease, because we believe that these are the initiating regions for bronchitis. And this is because this is where the pollutants settle out. The cigarette smoke, for example, settles out, and this is where the bronchitis begins in these small airways. Okay, the third mechanism of deposition is diffusion. Now, diffusion rates for aerosol are generally small anyway, but once you get down to very small airways, less than 0.1 of a micron, then diffusion starts to occur, and this can be a reason why some aerosol can find its way to the alveoli. Not much of it, but the most peripheral regions of the lung can get some aerosol deposition by diffusion. Now, the load of pollutants that you take on depends on the level of ventilation. If you're a coal miner working at the coal face, working hard with drills or whatever, and have a high level of ventilation because you're exercising, then that is going to increase the degree of deposition of aerosol. Hyperventilation will do the same thing. Anything that increases the amount of air that's inhaled is going to increase the deposition of aerosol. Okay, now let's move from deposition of aerosol to the clearance of the deposited particles. And there are two quite separate systems for the clearance of particles in the lung, cleansing the lung, as it were. Very important. One is the mucociliary system, which we've already referred to 2 or 3 times in the airways, and the other is the alveolar macrophage system. So let's look at where these 2 systems occur. So the mucociliary system is mainly in the airways, or I should say is confined to the airways, I should say, because it certainly doesn't occur in the alveoli. The mucociliary system is in the airways. The particles are moved up by the mucociliary escalator, and then they're tipped over into the gastrointestinal tract at the epiglottis. Once they're in the GI tract, we can forget about them. So that's the mucociliary system in the upper part of the lung, the airway system of the lung. But in the respiratory region of the lung, there is no mucus, no cilia, and here we need a different mechanism, and that's the alveolar macrophages, which are roaming around the alveoli and engulf the particles. So let's look in more detail, first of all, at the mucociliary escalator. And I have to tell you, I think this is one of the most elegant things that evolution has provided us with. It's a very elegant way of moving pollutants out of the lung. And so what we've got here is a system where we have mucus sitting on top of or being propelled by cilia here. And the dust particles fall onto the mucus layer, they're trapped there, they can't get off, and they're moved up to the, in this case moving from left to right, moving up from the lower parts of the lung up to the epiglottis. Where does the mucus come from? Let's ask first of all. Well, it comes from 2 sources. It comes from mucus, or sometimes called seromucous glands, deep in the airway wall, which you can see here, and then there's a duct that takes the seromucous material up to the airway wall. They also come from goblet cells, and we've already mentioned both of these. But let's look at them in a bit more detail. Let's look at the mucus glands. Here's a section, this is just a drawing of the airway wall, and you can see the airway epithelium here. This is the lumen of the airway here. Here's the airway epithelium here, and here's most of the wall of the airway, and then the cartilage below it here. And you can see in the middle of the wall of the airway, we have this mucus or seromucous gland. It produces 2 kinds of material, a serous material and a mucus material, and that's why it's sometimes called seromucus. And there are ways of measuring the amount of these glands using an index here, which I'm not going to go into, because the increase in size of these mucus glands is the hallmark of chronic bronchitis. In fact, let's look now at what happens in chronic bronchitis. First of all, at the top here, and it's not as clear as it might be, but this is the top airway here. Here's the epithelium here. This is the lumen of the airway here. The epithelium of the airway. Here's most of the wall, and here is cartilage. And you can see in the middle of the airway, as we saw on the drawing before, there's this relatively thin layer of mucus glands. But now look what happens in severe bronchitis. Here's an airway from a patient with severe bronchitis. The lumen of the airway is here, and you can see that most of the airway wall is made up of these greatly hypertrophied mucus glands. So what happens in chronic bronchitis, and here's, this is the cartilage below. So what happens in chronic bronchitis is that the smoker, as he almost always is, the smoker inhales cigarette smoke. This damages the airway, and it provokes a great increase in the amount of mucus glands. They're trying to produce mucus, if you like, trying to produce mucus so that this inhaled pollutant can be removed by the mucociliary escalator, and in the process you get this tremendous enlargement of mucus glands in the airway wall. And incidentally, this is part of the reason why the airway wall is thickened in chronic bronchitis. You also get edema of the airway wall, And that's one of the reasons why the airway resistance is increased. So that's what happens in chronic bronchitis. The other source of mucus, and we've mentioned this before, is the goblet cell. In fact, actually in the first session, I showed this particular image. It's a very lovely image. It's done by scanning electron microscopy, and you can see the goblet cell here. You can see the hole through which the mucus is being extruded onto the airway wall, and around here you can see the cilia. So very, very pretty picture indeed. So let's look in more detail then at the mucociliary escalator. The first point to make is that the mucus actually has two layers. It has a superficial layer called the gel layer, which is jelly-like, if you like. It's rather viscous and thick, and when particles fall on it, they're completely trapped. There's no way they're going to get away from the gel layer here. But this gel layer probably would not work for the whole of the escalator because you couldn't get the cilia to work in it. It's too thick. And so below the gel layer is what's called a sol layer, which is much less viscous, and it's within this layer that the cilia work. And you see they're pushing in this direction, and what happens is that the tips of the cilia touch the bottom of the gel layer and move it along. It's a bit like somebody in a river with a raft above on the surface of the water, and he's in the river and he's pushing the raft by touching it with his hand under the water. That's the general idea. So this is the way the mucociliary escalator works, and it's a very effective way of doing this. The cilia are about 5 to 10 microns long. They beat about 20 times per second, 20 hertz if you like, and they're very effective in moving this layer here. One thing that may occur to you if you think about it is, now what's going to happen as all this mucus comes in from the periphery of the lung? Got a vast area of the airways in the periphery, and it's all converging on the large airways in the trachea. Well, what happens is that the rate at which the mucus is moved has to increase a lot. And it goes at about 1 millimeter a second in the very, very low airways, and goes up to, one millimeter per minute, I meant to say, in the smaller airways, and then goes up to something like 2 centimeters per minute in the larger airways. And to me, it's very remarkable that this system works so well. You may think that all the mucus would pile up in the larger airways because it's converging from so many regions, but obviously the thickness of the sol layer has to be controlled very accurately because you must have the tips of the cilia just touching the sol layer and moving it, and so it's really a very good, elegant way of doing this, and we don't fully understand the complete regulation of the mucociliary escalator. I don't think anybody knows precisely how the body manages to maintain the thickness of the sol layer at just the right level so that the cilia can move it along. It's a very remarkable arrangement indeed. Actually, I've got a couple of nice nice micrographs here. Now this one is not so nice, I think, particularly, but I'll show it to you. This is the mucus layer here, just here. Here you've got the epithelium here, the epithelial cells, and you've got the cilia here, and you can see that there are 2 layers to the mucus. There's a very dark layer on the this is the lumen of the airway, so towards the lumen you've got the gel layer, very dark staining, and then you've got the sol layer with the cilia working within it. Actually, a much better slide is shown here. Here's an electron micrograph, very pretty electron micrograph, and now you can see the airway epithelium here, and you can see the cilia here, because usually you don't cut a cilium all the way along its length. It would be very remarkable to do that. So you're cutting across them to some extent, but you can see the cilia here, and notice how they're just touching this upper layer, the gel layer here. And incidentally, you can see that the gel layer is more electron dense than the sol layer, which I think would fit with the fact that it is stickier, more viscous, got more stuff in it. So that's the gel layer, and this is the sol layer. This is the airway epithelium here, and I suppose this may be a goblet cell. It certainly looks as though it might be that. The ciliary action is shown here. Now here we're going from right to left, and what happens is that on the forward stroke, the cilium moves like that, like an extended arm, but then on the backward stroke, the arm is flexed at the elbow, if you like, and comes back and then goes forward again. So the ciliary action itself is pretty complicated, and hats off to evolution who managed to work that out. Here's the structure of a cilium, and I see now it says structure of a microtubule, and it really should say structure of a cilium, which is made up of a series of microtubules. Okay, this is a very high magnification. Here's an electron micrograph here, and the cilium is made up of a series of microtubules. Well, I suppose it shows the structure of the microtubules as well. There are a series of microtubules. There is a doublet in the center, and there are a series of doublets around here. And the way that the cilium bends is that you have contractile proteins in the microtubules. You have two of them, and they contract more on one side than the other, and that bends them over. That's the way it works. And I show this partly because there are things called dynein arms that I'm certainly not going to go into, and I certainly don't understand, but there are dynein arms attached to the, or integral with the microtubules. And you can see that if you look closely here, the dynein arm here, another one here, and so on. These are dynein arms, and I point that out because there is a congenital abnormality, congenital disease, where there's an absence of dynein arms, and the cilia then don't work properly. That's called ciliary dyskinesia. Not working properly is what that means, ciliary dyskinesia. And that's a cause, as you might expect, of chronic lung disease. If the cilia aren't working properly, then the mucociliary escalator is not able to work properly, and so this is part of the reason why this is a reason, one reason why the mucociliary escalator can go wrong. Very nice picture, difficult to see on the electron micrograph, although it's a very good one, because these are terribly small things, but beautifully shown on the diagram to the left there. Now the normal mucociliary escalator can become abnormal under various conditions. And one condition I've already referred to briefly is that it can be too much mucus. And that's what happens in chronic bronchitis. In chronic bronchitis, the load of pollutants from smoking cigarettes or whatever is such that the mucus glands produce so much mucus that the escalator just cannot deal with it. I mentioned, how important apparently it is that the thickness of the sol layer be just right. Well, if you produce enormous amounts of mucus, you completely overcome the ability of the mucociliary escalator to move the stuff, and that's why patients with chronic bronchitis will cough up secretions. And you get a lot of what are called retained secretions in the lung. That's one of the important features of chronic bronchitis. In fact, we define chronic bronchitis based on the fact that people are coughing up secretions, coughing up large amounts of mucus. So this occurs in chronic bronchitis. There's too much mucus. Cystic fibrosis is another disease, congenital disease, and in that case the mucus is abnormal. The composition of the mucus is abnormal, and the patients have a hard time getting rid of it. The same is true in asthma. In asthma, we don't normally think of asthma as being associated with a lot of mucus, but it turns out that the mucus in asthma is very difficult to move. For some reason it's very viscid, and patients with asthma will sometimes cough up plugs of this material called Kirschmann spirals. They cough these things up. You can see them in the sputum. And so one of the problems with asthma is the change in the characteristics of the mucus. The cilia can become, their function can be abnormal. They can be paralyzed by toxic gases. You know, there are many gases that people are exposed to inadvertently. Cigarette smoking, of course, is one, but quite apart from that, for example, there are a number of accidents caused by by chlorine. Every now and again you can read about a tank. Chlorine's used a lot in industry for various reasons, and the chlorine is transported by big tanks, and occasionally one of these will fall over, eliminate chlorine, and cars will go through the chlorine cloud, and people will become will be affected by the chlorine. In fact, chlorine was used during World War I as a war gas, you may recall. So, and these gases tend to paralyze the cilia. Also, you can have a situation where the bronchial epithelium is destroyed. Actually, that happens with the common cold sometimes. You know, when people have a serious cold, they say, "Oh, it's gone to my lung." And sometimes when that happens, they have some acute bronchitis, and the bronchial epithelium may be destroyed for a period. It will always come back, but it's destroyed for a period, and then the patient has a hard time getting rid of the secretions. And I've already mentioned the congenital defect of ciliary motion, ciliary dyskinesia, which is it's not a common condition, but it's a condition where the cilia just don't work because the structure of the cilia is abnormal. Okay, so that's the mucociliary escalator. Now let's talk about the cleaning of the alveoli, because as I said before, there are no cilia in the alveoli, and there's no mucus in the alveoli. There's surfactant in the alveolar lining layer, but don't get confused. Surfactant and mucus are entirely different. They're not related at all. And so the alveolus has to find another way of keeping itself clean. And it does that using the alveolar macrophage. Now, the alveolar macrophage is an amoeboid kind of cell. It roams around the surface of the alveoli, puts out pseudopodia, roams around, and it engulfs, it phagocytoses anything it comes across that shouldn't be there. And so it's a very effective way of keeping the alveoli clean. Actually, this is a beautiful scanning electron micrograph. It shows the macrophage very beautifully here. And what do you think this is over here? Well, I think that's a type 2 alveolar epithelial cell. It's certainly got a row of microvilli around it, and that's almost certainly what it is. And then over here, you've got the regular type 1 cells, type 1 alveolar epithelial cell. And here's another picture of an alveolar macrophage. Actually, we've seen this before, but it's very pretty, and we'll have another look at it. Initially, you may have a hard time working out what indeed you are looking at, but here is the macrophage here. This cell is the macrophage. Here is its nucleus. Here's the cytoplasm. And in the cytoplasm, you can see that it's engulfed various bits and pieces. Here's the wall of the alveolus here, running along here, and then running along here, and another wall is going here, downwards. And so what you've got is a macrophage lurking in the corner of the alveolus. And it has engulfed various particles, including these very electron-dense particles, which are remnants of surfactant. Because, and you can always recognize surfactant, it has this onion skin kind of appearance, a series of whorls, and this is remnants of surfactant. Surfactant turns over rapidly. In a day or two, you lose your surfactant unless you keep replenishing it. For example, in a disease like pulmonary embolism, if part of the lung loses its pulmonary blood flow, then you're likely to have the surface tension of that region increase, and the lung may become atelectatic, may become collapsed. So surfactant turns over rapidly, and you can see here that the macrophage has picked up some of the remnants left over. it's important to keep the alveolus clean. Okay, so that's the macrophage system. Again, a very effective way of keeping the alveoli clean, and as I say, quite different from the mucociliary escalator. Impairment of normal macrophage function. I should definitely talk about that. The macrophages can be affected. For example, they can be affected by cigarette smoke. Other inhaled gases can do this, apparently. Ozone can affect macrophage function. It's interesting that if you do what's called bronchoalveolar lavage, now that means you put a bronchoscope into somebody's lung and you put some small amount of saline in, and then you pull it back again and you have a look at the lavage material, what you've washed out with the saline. You look at someone who is a non-smoker and the macrophages look very pretty. Look in a smoker's bronchoalveolar lavage fluid, the macrophages look terrible. They're all brown and black, and obviously they've been picking up bits of cigarette smoke and so on. So they're in terrible shape. So inhaled gases apparently can affect macrophage function. The macrophages are very effective at phagocytosing matter that should not be there, but sometimes that material is toxic, and that's the case with silica. Silicosis is a disease which occurs in people who work with silicon dust, with sandblasting. Now, in this country, that is controlled very carefully with respirators and ventilation and all the rest of it. But in some third world countries, that's not the case. And people develop severe silicosis. It's a very unpleasant disease, rapid impairment of lung function with a lot of laying down of collagen in the alveolar walls. It's one of the causes of interstitial lung disease, and silica is a very toxic material. And so what happens is that when the macrophages pick up the cilia, that kills the macrophages, and sometimes they can affect parts of the lung. And then we've got alveolar hypoxia, which also impairs normal macrophage function, apparently. Radiation sometimes does that. You know, radiation occasionally occurs in a lung by mistake, inadvertently. If someone has a carcinoma of the breast, for example, irradiated, normally you protect the lung, you shield it, but sometimes the radiation affects the lung, and you can get impaired macrophage function, and there are other causes as well. So let me now just summarize where we've been with this whole question of defenses of the lung. Very important feature of the lung has to do with atmospheric pollutants. We went through the various kinds of pollutants and noted that the largest one by weight is carbon monoxide, but there are a number of other unpleasant things as well, including the oxides of sulfur and nitrogen and particulate matter, and particularly the smog, which is caused by this photochemical process where you end up with these very unpleasant gases such as ozone and so on, and they are highly toxic. We talked about the danger of cigarette smoking, because in terms of inhalation of pollutants, cigarette smoking is far more dangerous than walking around in the polluted area of a big city. The concentration of pollutants is much greater, and we pointed out that the incidence of carcinoma of the lung has increased tremendously over the last 50 years or so, but fortunately there's some evidence at least that it's declining now, and we all have a responsibility to try and persuade people not to smoke. We looked at the three mechanisms of deposition of aerosol, and they were impaction, sedimentation, and diffusion. And we looked at, and each of those particularly affects different sized particles. Impaction, the very large particles; sedimentation, the medium sized; diffusion, the very small sizes. And impaction is responsible for the nasopharynx picking up essentially all the large particles. The the medium-sized particles tend to deposit in the small airways, a very important factor in the development of bronchitis, we believe, and occasionally some of the very smallest particles get to the alveoli. We talked about the clearance of these deposited particles, the mucociliary escalator, what an elegant system it is, and how carefully regulated the whole thing must be. We don't fully understand how it's done, but the normal mucociliary escalator works very well. However, you can have problems with the mucociliary escalator, particularly in a disease like chronic bronchitis, where there's tremendous enlargement of the mucous glands. They produce much more mucus than the escalator can handle, and so the patient has got retained secretions that he has to cough up, and it's a very inefficient way of clearing the lung. We then talked about the alveolar macrophage system, again a very elegant system, but again that can be affected by the inhalation of toxic gases. So that's the end of our discussion of the defense systems of the lung, and hope to see you next time.